So, good afternoon, everyone. Welcome to the second session of group theory and chemistry. So, morning we were discussing about the symmetry elements and the symmetry operation. So, we are continuing the second session into improper axis. I welcome each and everyone present here to this webinar. Thank you, each and everyone, for your patience. As Sar mentioned, Chitra Sar mentioned, patience is the real key for group theory, practice and patience. Okay, I hope each and everyone to learn from him. And okay, thank you.
This is presentation number 3, symmetry elements and symmetry operations. The part 3, improper rotation axis Sn. Contents, improper rotation axis Sn, the S2, S3, S4, S5, S6 and S10. The illustrative examples, I will use these molecules: trans-dichloroethylene, eclipsed ethane, staggered ethane, eclipsed furosane, staggered furosane, and if time permits, methane. Then operation generated from even order Sn axis. Then operation generated from odd order Sn axis. These are the contents of this presentation. Improper rotation axis Sn or rotation reflection axis or alternate axis of symmetry. Suppose a molecule is rotated about an axis through some angle and the resulting configuration is reflected in a plane perpendicular to this axis. So a molecule rotated about an axis through some angle and the resulting configuration is reflected in a plane perpendicular to this axis. If the new configuration is indistinguishable from the original, then the axis is called the improper rotation axis or rotation reflection axis and denoted by the symbol Sn. The axis about which the rotation is affected need not necessarily be a proper rotation axis. Sometimes it will be a proper rotation axis, and many times it won't be a proper rotation axis. So the axis about which the rotation is affected need not necessarily be a proper rotation axis. The improper rotation axis is designated by the symbol Sn, where n is equal to 360 by theta, just like the Cn. Theta is an angle, n is called the order of the axis. Then, if it is 180, this is S2, 120, S3, then S4, S5, S6. Additionally, we have got the S10, where n is equal to 10 and theta is equal to 36. Then illustrations. You follow this carefully. S2 axis, trans dichloroethylene. Trans dichloroethylene. This is a model of the trans dichloroethylene. This is a model of the trans dichloroethylene. This is a photograph of the trans dichloroethylene molecule. The two chlorine atoms are trans to each other. This molecule is planar. This is diagrammatic represented like this. And this axis I take as a Z axis. This as a X axis, this as a Y axis. Even though this is not a symmetry axis, I'm taking this as the Z axis. Now, so this is Z, this is X, this is Y. Suppose this molecule is rotated about the Z axis through 180 degree and the resulting configuration is reflected in the plane perpendicular to it. That is the XY plane. So rotated about the Z axis, reflected in the XY plane. Let me label the two hydrogen atoms as 1 and 2 with a blue color. Chlorine as 1 and 2 with a red color. When you rotate it through 180 degree about this axis, what will happen? These two will be interchanged. That the chlorine 1 and the hydrogen 1 will be interchanged, and the H2 and the Cl2 will be interchanged. Hope we can visualize that rotation. Then this is a resulting configuration. So this is H1, this is Cl1, this is H2 goes here, Cl2 goes here. Now, this is a plane which is perpendicular to the C2Z. So, this is a sigma xy plane. Now, you reflect about this plane. Now, the Cl1 and the H2 will be interchanged. And the H1 and the Cl2 will be interchanged so that you get this configuration. The H2 comes here, Cl1 comes here. The Cl2 comes here, H1 comes here. Now, let me number these three configurations as 1, 2, and 3. Now, you compare the configuration 1 and 2. Are they distinguishable or indistinguishable? Hydrogen 1, Cl1. So, they are distinguishable. Therefore, the rotation about the z-axis through 180 degree is not a symmetry operation. And hence, the C2 is not a symmetry element. So the C2 is not a symmetry element. Now you compare the configuration 2 and 3. You've got a Cl1, H2. They are distinguishable. Therefore, the reflection about the XY plane is not a symmetry operation. Hence, sigma is not a symmetry element. Now you compare the configuration 1 and 3. You've got a hydrogen, 1 on the left, hydrogen 2 on the left here, then Cl, Cl, H. So these two configurations are equivalent configuration. Even though they are not identical configurations, they are equivalent configurations, and these two configurations are indistinguishable. So the rotation about the z-axis followed by reflection in a perpendicular plane is a symmetry operation. The symmetry element corresponding to these combined operations is denoted as S2 because the angle, the theta is 180 degree. So, trans-dichloroethylene molecule is an example of a molecule which has got a S2 axis of symmetry. Then S2 operation is a very important result, produces the same result as the inversion I. That is S2 is equal to I. This is a very important relationship. So this is S2, what I had just shown. Then inversion I, the same molecule, if you invert it, these two will be interchanged. So this is Cl1, this is Cl2, this is H2, this is H1. Let me number these as 1 and 4 because this is the same molecule. Now, 1 and 3 are what? They are indistinguishable, they are equivalent. Then 1 and 4 are also the indistinguishable and they are the equivalent. Now we compare the 3 and 4. The 3 and 4 are identical. This is 2, this is 2, 2Cl. So these two are identical. So the S2 operation produces the same result as the inversion operation I. So we conclude that S2 is equal to I. This is a very important relationship. Now S3 axis eclipsed ethane. Say this is a eclipsed ethane molecule. These two hydrogen against each other. With the model, I can easily show the presence of the S3. Suppose I rotate it through, S3 means rotation is through 120 degree. Rotate it through 120 degree. I will get this configuration. Then reflect it. This half will come here, this half will go there. So that's a symmetry operation. The rotation followed by reflection is symmetry operation. Let me show this diagrammatically. This is eclipsed ethane. Then the hydrogen atoms are labeled 1, 2, 3, 1 prime, 2 prime, 3 prime. Rotated about this axis through 120. What will happen? This will become 3, 1, 2. This is 3 prime, then 1 prime and the 2 prime. Then reflecting. Visualize the resulting configuration. You try to visualize the resulting configuration. These two will be interchanged. The hydrogen label 2 will be interchanged. Likewise, hydrogen atom 1 and 1 prime will be interchanged. So this segment will come here and the segment will go there. Now, 1, this is 2, this is 3. Now we compare the configuration 1 and 2. Are they distinguishable or indistinguishable? They are indistinguishable. Therefore, the rotation about the z-axis through 120 degree is a symmetry operation, and hence C3 is a symmetry element. This was not the case with an S2 axis. Now, you compare the configuration 2 and 3. They are also indistinguishable. Therefore, the reflection about the xy plane is a symmetry operation, and so sigma is a symmetry element. Now we compare the configuration 1 and 3. They are again indistinguishable. Therefore, the rotation about the z-axis followed by reflection in the perpendicular xy plane is a symmetry operation. S2, S3 and S3 is a symmetry element. So here the S3 axis C3 and a perpendicular sigma also exists independently. This is the property of an odd order SN axis. S3 is an odd order SN axis. If an odd order SN axis exists, a C3 and the sigma must exist independently. But in the case of the even order, the Cn and the sigma will not exist independently. Then S6 axis, staggered ethane. This is a staggered ethane. You wrote this is staggered ethane. This is S6. So rotate it through 60 degree. Then this will come here. The 2 will come here. This 3 will come here. So this is the configuration. Then you reflect it in this plane. This segment will come, fragment will come here. This fragment will go the other side. So you get this configuration. Now you compare the configuration 1 and 2. The configuration 1 and 2 they are distinguishable. Therefore, the rotation about the z-axis through 60 degrees is not a symmetry operation, and hence the C6 is not a symmetry element. Now you compare the 2 and 3. They are indistinguishable. Sorry, they are distinguishable. Therefore, the reflection about the xy plane is not symmetry operation. This is not a symmetry operation. Sigma is not a symmetry element. Now we compare the 1 and 3. They are indistinguishable. So, the rotation about the z-axis through 60 degree followed by reflection the perpendicular plane is a symmetry operation, and S6 is a symmetry element. Here S6 exists, but the C6 and the sigma do not exist independently. Now we have just seen that the eclipsed ethane has an S3 axis, staggered ethane has an S6 axis. And this is what is called the eclipsed ferrocene. In the eclipsed ferrocene, the Fe2 plus ion is sandwiched between two eclipsed cyclopentadienyl anion. Note that this is against this. So this is eclipsed. If eclipsed ethane has S3 axis, what should be the SN axis in the eclipsed ferrocene? Note that cyclopentadienyl anion has a C5 axis. So then this is a staggered ferrocene. Then if this is S3, this will be S5, this will have S10. So the example of a molecule which has got a S5 axis is the eclipsed ferrocene. You can relate it to eclipsed ethane. And the example of a molecule with the S10 axis is staggered ferrocene, which can be correlated with the staggered ethane. So that the PTCl4 2 minus has S4, C4, and the sigma. And the benzene has S6, C6, and the sigma. This is very, very important. See, identity can generate only one operation. Cn can generate n operation. Sigma can generate two operations. Sigma and identity, then I can generate two operations, I and identity. Now we are going to consider the operation generated by Sn. Before you proceed further, let us refresh your memory by recalling the following results. See, e to the power n is equal to e, whether n is odd or even. Cn to the power n is e, whether n is odd or even. Sigma to the power n is e, if n is even. And the sigma to the power n is sigma, if n is odd. Then C2 into sigma is equal to S2, which is equal to that. If you want, you can jot it down. Then C4, 2 is equal to C2. Then C6, 2 is equal to C3. Then C6, 3 is equal to C2. C6, 4 is equal to C3, 2. Cn, n plus 1 is equal to Cn. Cn, n plus 2 is equal to Cn2. Because if the superscript is less than the subscript, divide both by the common factor. That's what we have done in these four operations. And if the superscript is greater than the subscript, subtract the subscript from the superscript. Remember this. An operation generated by Sn. See, the number of operations generated by Sn depends on whether n is odd or even. An even order Sn axis generates n operation, whereas an odd order Sn axis generates 2n operations. Remember this, an even order Sn axis generates n operations. An odd order Sn axis generates 2n operations. To find out the number of operations generated by Sn, we perform the operations Sn, Sn2, Sn3, etc. until we arrive at the identity operation. To find out the number of operations generated by the Cn, say for example C3, C3, C32, then C33 identity. Stop with the identity. Likewise, start with the Sn. You stop when you arrive at the identity operation. Symmetry operation generated by even order Sn axis. S2, S4, S6, S10, etc. An even order generates n symmetry operations, namely Sn, Sn2, Sn3 up to Sn, which is identity. Let us prove that Sn n is equal to identity when n is even. The Sn means the Cn sigma, Cn sigma, Cn sigma, and so on until each operation is carried out n time. So I can write Sn n is equal to Cnn sigma to the power n. We know that Cnn is equal to identity, whether n is odd or even, and sigma to the power 1, n is e, since n is even. Therefore, Sn to the power n is equal to e into e is equal to e when n is even. Also, Sn n plus 1 is equal to Sn n, then another Sn. And the Sn n is identity in the Sn, which is Sn. Sn n plus 2 is equal to Sn n, Sn2, which is Sn2, and so on. Now, S2 axis can generate how many operations? The two operations, namely S2 and S2, 2. S2 is equal to C2 into sigma, which is I, which is already proved. S22 is equal to C22 sigma 2, which is E into E is equal to E. So, the two symmetry operations generated by S2 axis are I and E. Note that the operations generated by S2 do not include C2 and I. We don't have the C2I among this operation. We have I and E, we do not have C2 and the sigma. Then S4 axis. Four symmetry operation, namely S4, S42, S43, and S44. Some of these operations may be expressed in other forms. Then S42 is equal to C42 into sigma 2, then C2 in the identity C2, then S43 is C43 sigma 3, which is C43, this can be written as sigma, which cannot be written any other form. And S44 is C44 sigma to the power 4, which is equal to identity. So the four operations are, this is S4, then C2, then S43 and identity. S4, C2, SO3 and identity. Note that the operations in S4 do not include C4 and the sigma. And this you can try the 6 operations generated by S6. You just write down this result. S6, C3, I, C32, S65 and identity. These are the 6 operations generated by the S6 axis. How you arrive at this result is given here. You try it. So this, then finally you must end up with this. The operator do not include C6 and sigma. Then let's not bother about this. Then S10. Write down all the symmetry operations generated by S10 axis and show that the S10 axis is coincident with the C5 axis. That is, you generate all the operations, 10 operations using the S10. These 10 operations will include the 5 operations generated by C5, namely C5, C5-2, C5-3, C5-4, and identity. Now operation generated by odd order SN axis, S3 and S5, we'll discuss. An odd order SN axis generates 2n operations, namely SN, SN2 up to SNN, which is not identity, then Sn n plus 1, Sn n plus 2, etc. up to Sn n. I'm sorry, this is the 2n. Sn 2n, that's a mistake here. Some of these operations may be written in other forms. S3 axis can generate 6 operations, namely S3, S32, S33, S34, S35, and S36. That is twice this order. Now, some of these operations may be written in other forms. I will do this one. Do this once. S3 is C3 into sigma. Then S3, this cannot be written in any other form. Then S32 is C32 into sigma to the power 2, sigma to the power identity. So this is C32 into identity is equal to C32. Then S33 is C33 into sigma to the power 3, C33 is identity. This is sigma, so this is sigma. So S33 is sigma, whereas S22, S44, etc. are identity. Then S34 is C34 sigma to the power 4, which is C3, into identity, which is C3. And S35 is C35 into sigma to the power 5, which is C32 into sigma, cannot be written any other way. Then S36 is equal to C36 sigma to the power 6, which is C33 into identity. Then C33 is identity, so the final result is identity. So the 6 operations generated by the S3 are S3. Then C32 sigma C3. Then S35 and identity. You list all these operations. S3, C32, then sigma C3, S35 and identity. Now look at the 6 operations. S3, C32, sigma C3, S35 and identity. The C3, we find that this S33 is sigma. It follows that sigma is a symmetry element by its own right. And the mirror plane sigma associated with this operation must be a symmetry element by its own right. This is not the case with an even order SN axis. Then C3, C32 and identity are the operations generated by the C3 axis. That means the S3 axis is coincident with the C3 axis. The S3 axis also is C3 axis. Thus we find that if an S3 axis exists, a C3 and the perpendicular sigma must exist independently. But if an odd order SN axis exists, the CN and even order SN axis exists, CN sigma will not exist independently. This particular result will be used when you assign point group to certain molecules. Yes, fine. You write down all the 10 operations generated. You can note down this if you want. The final result. S5, C5-2, S5-3, C5-4, sigma C5, S5-7, C5-3, S5-9 and identity. If you are able to arrive at these results, that simply means that you have got a good hold of the symmetry operations.